Good morning everyone. So, we are looking into the gas separation by membrane based separation processes, and in the last class we have discussed about various modes of gas separation by membranes. Depending on the type of flow or flow configuration, one can have a cross flow type of separation system, one can have a counter current flow, one can have a co-current flow. So, in the last class we have talked about a super mixed system, that means a system that is really called really acts like a CSTR. That means the gas velocity is so high that in fact one can put stirrer in the feed stream as well as in the permeate chamber, so that the streams are really mixed. So, one can assume a completely star tank reactor model in order to develop the design equation of this type of systems. Now, in today's, so and we have already derived the design equations based on the star tank reactor model for a completely mixed system, and we have seen that there are around 7 variables that one can have in such a system. Now, out of these 7 variables, 3 or 4 are known, and rest of them can be one can determine, and there are several types of unknowns. Maybe it may be that the fractional recovery in the permeate or the permeate concentration or jet concentration, mole fraction, in terms of mole fractions, they may be known or they may be unknown. Now, out of these 7 parameters, 4 are known and 3 are unknown. So, one can use the design equations, and there are 3 number of equations and there are 3 unknowns. So, it is a totally solvable system, and one can predict the system performance. Now, in today's class we will talk about another mode of flow configuration in gas permeation, that is the cross flow model for gas permeation through a membrane. Okay. So, let me draw the schematic of this. This is the feed is coming into the system at high pressure, feed in high pressure, and the flow rate is QF, the mole fraction is XF, pH is the pressure in the feed side is a high pressure, PL is the lower pressure, and the permeate is taken out from the other side, and this QP is a fraction of QF. So, that fraction is the theta, that is the cut of feed, that is the percentage of feed that is going into the permeate, and it is a low pressure side. Often the permeate side is attached to a vacuum, so that a low pressure is maintained, and there is a substantial pressure difference across the membrane that drives the solute to move from the feed side to the permeate side. Y is the concentration is the mole fraction of the required desired component in the permeate side, and the permeate is really moving into the permeate side by a cross flow. Why it is a cross flow? Because the reject is the feed stream is going into the permeate is going in normal to the direction of the feed flow. So, the reject side will be having a composition a mole fraction x naught, and it will be having a q naught, which is nothing but 1 minus theta times QF. Okay. Now, if you consider a differential element in the feed chamber, that it is located between a membrane area of DAM, and at the location x, Q is the the location L, Q is the flow rate and x is the mole fraction, and L plus delta L the flow rate, since some amount of permeate is going away to the permeate. So, flow rate will be really decreasing, and at the exit of the differential element, the flow rate will be Q minus dQ, and the mole fraction will be x minus dx. Why these will be negative? Simply because as you go along the length of the membrane, the feed flow rate will be decreasing, because some amount is already moving over to the permeate side. and similarly some amount of the component, the desired solute, that will be also moving into the permeate. So, the mole fraction will also be decreasing. So, x minus dx will be the mole fraction at the exit of this differential element, and q minus dq is the flow rate that is at the exit of the differential element. Now, what we are assuming? We are assuming, let us list down the assumptions. Assumptions are: number 1, the feed side velocity is high, enough to have a plug flow. Okay. Secondly, the permeate, there is no mixing, in feed and permeate. Okay. So, there lies the difference between this model and the earlier model. In the earlier configuration, we have assumed that there is complete mixing up of the feed side as well as in the permeate side. So, we assumed a completely start tank model or completely mixed up model. In this case, it is a plug flow. Therefore, at every location of the membrane length, the feed, the flow rate as well as the composition will vary. Okay. Now, over a differential membrane area dm, dam at any point, local permeation rate is given as for component A, and what is the local permeation rate? Local permeation rate will be nothing but the permeability of this particular species multiplied by the driving force. What is the driving force? Driving force is the partial pressure of that particular component in the feed side minus the partial pressure of that particular component in the permeate side. So, minus y dq is equal to P A prime divided by T P H x minus P L y d A m. Okay. So, T is the thickness of the membrane, P A prime is the permeability of species A through the membrane. Let us write down this equation number 1. For component B, you can have a similar balance minus 1 minus y dq is P B prime by T P H 1 minus x. So, it is we are considering it is a binary mixture of A and B minus P L 1 minus y d A m. This is equation number 2. Now, these two and dq is the, what is dq? dq is the total flow rate perpendicular to the differential element dm. Flow rate perpendicular to the differential element dam. Now, you can divide this equation number 1 by 2 and see what you get. If you divide equation number 1 by 2, you will be getting as 1 minus y is equal to alpha star x minus P L over P H multiplied by y, 1 minus x minus P L over P H into 1 minus y. Okay. Let us say this is equation number 3. And what is alpha star? Alpha star is nothing but the ratio of P A of permeability of component 1 component A and that of the permeability of the component B. The permeate composition y is varying and the reject composition x, mole fraction x, that varies as a point function throughout the length of the membrane. So, y and x, that is y is in permeate and x in feed or reject, they are point functions. What do you mean by point functions? Because they are varying as a function of length along the membrane. Vary along the length of the membrane. Okay. Now, all this if you really solve this differential equation, now I am not going to solve the differential equation in this class, because that is not the purpose. It is a big huge derivation. Now, I am just writing the analytical solution, and I will be finally writing the design equation for this particular cross flow system. So, this system is solved. I mean, you have to solve y dq is equal to P a prime by T P h x minus the equation number 1 and 2 in the differential form. Okay, that we have written down, that those two equations have to be solved simultaneously, and the analytical solution that you are going to get after solution, I am just writing the design equation. Okay. The design equations are given as one minus theta star into 1 minus x divided by 1 minus x f is equal to u f minus e over d divided by u minus e over d raised to the power r u f minus alpha star plus f divided by u minus alpha star plus f raised to the power s multiplied by u f minus f divided by u minus f raised to the power t. This is a huge expression, and all these symbols, they have different meanings. Let us write down what are the meanings. Theta star is 1 minus q by q f. Okay. So, q is the feed that is going into the permeate, and q f is the feed that is getting into the system in the reject stream. We define a quantity called I. I is defined as x divided by 1 minus x. Basically, this is the mole fraction in the reject stream of this is the ratio of the mole fraction in the reject stream of component A and component B. Okay. And u is given as minus d times E I plus under root d square I square plus 2 E I plus f square. And what is d? D is 0.5 1 minus alpha star times P low divided by P h plus alpha star, that is d. And what is E? E is alpha star by 2 minus d times f. And what is f? F is minus 0.5 into 1 minus alpha star P L by P h minus 1. So, your basic parameters were the operating condition P L, P h, properties of alpha star. So, all these things will be can be expressed in terms of the known values, and there are some more parameters. R is given as 1 over 2d minus 1, and what is S? S is alpha star times d minus 1 plus f divided by 2d minus 1 alpha star by 2 minus f. And what is T? Capital T is nothing but 1 over 1 minus d minus E by f, and what is u f? U f is value of u at I is equal to I f, and what is that? That is I f is equal to nothing but x f divided by 1 minus x f. That means at the feed conditions. Now, composition at the exit of the feed stream is given as at exit x is equal to x naught, that is the reject composition finally that is going out. Theta star is cut ratio fraction of feed that is permeated, okay, and Y p is the mole fraction at the exit of the permeate is estimated by the overall material balance. Composition of permeate is calculated by overall material balance. Balance, that is Y p, you can calculate using that. What is overall material balance? Net amount of A going into the system in, and what is the net amount? Q f multiplied by x f. Okay. Net amount of A going out at the steady state, A going out. There are two components, one is by the reject stream, another is by the permeate. So, it will be Q p multiplied by Y p plus Q f minus Q p, that is the reject stream multiplied by x naught, and Q p is nothing but theta times Q f, that the theta is the cut ratio, the percentage of a fraction of feed that is going into the permeate. So, if you do that, Q f x f will be nothing but Q p Y p plus Q f 1 minus theta x naught. X naught you have calculated, just we have written earlier. So, Y p is nothing but Q f x f minus Q f 1 minus theta x naught divided by Q p. Okay. So, Q p is again Q p is nothing but Q f into 1 minus theta. So, Q f will be cancelled out. So, x f minus 1 minus theta times x naught divided by theta. So, that is the composition of the desired solute, that is the solute A in the permeate stream, that can be obtained by overall material balance. Okay. Now, how will you obtain the membrane area required? The design equation for required area of the membrane for required area of membrane is given by this expression, A m is equal to T times Q f divided by pH P b prime. So, this is the pressure at the higher in the feed side from I naught to I f 1 minus theta star 1 minus x divided by f I minus I 1 over 1 plus I minus P L by P h 1 over 1 plus f of I f into I d I. where f of I is given as d I minus capital F plus under root d square I square plus 2 E I plus F square, and your T is the thickness of membrane, your P B prime is the permeability of species B through the membrane. So, this is the design equation for the membrane area required for such a system. So, given the operating condition, you can calculate and the target of removal, you can calculate the various values, and this integral has to be evaluated numerically by using trapezoidal rule or Simpson's rule. Okay. So, that is how the calculations or design of any cross flow system will be done. So, in the last class we have seen the completely mixed up system, in today's class we have seen the cross flow system. Now, I will go through one more system analysis, that is for the counter current application or counter current configuration. That will be very important, because out of all these configurations, the counter current will be the most efficient, because in the case of counter current you are allowing a neutral stream that is moving that moves in the opposite direction of the feed in the permeate, that is called a carrier gas, for example, nitrogen or helium, so whatever. Now, this carrier gas takes up the species A and it moves in the opposite direction of the feed. So, the concentration difference, the partial pressure, it is maintained at the maximum possible level. So, you will be getting the more permeation and the system efficiency will be enhanced significantly. So, counter current configuration is quite important. In this counter current gas separation, we will be having the two chambers separated by the membrane, and the feed is, this is the feed side, this is the permeate side. Okay. QF is the feed flow rate, XF is the feed concentration, and this is the mole fraction of the species A. Q naught is the flow rate of the reject stream, X naught is the composition of the reject stream. And in the case of permeate, you will be having Y I is equal to 0. It is going in the other direction. That means, it is a, when the carrier gas is entering into the system, there is no solute. So, it takes up the composition, the molecule species A, and it carries it away. Okay. QF prime is the flow rate of reject in the flow rate of the permeate that is going out, and Yp is its composition. Okay. That is a typical schematic of a counter current flow model. Now, we do a balance over a small element. These AM plus DAM, the differential element membrane area, and okay. So, Q is the flow rate at this particular location, X is the composition at this particular location, and we consider this end is located at the exit. Okay. So, AM will be equal to 0. That means, we start the calculation length from here. So, membrane length will be 0 here and it is going all the way up and we will be getting the full length of the membrane. So, AM will be the effective area of the membrane will be 0 there, it will be having some value AM at any x at any x location. Okay. So, yi, so Q naught is the flow rate of the reject stream, x naught is its composition, and it is coming as yi will be equal to 0, and at any location it is Q prime is the flow rate of the permeate stream and the composition is y. Okay. So, that is the notation we are going to use in this when we are doing a small elemental balance in the counter current flow configuration. Okay. Now, let us write down various design equations. Number 1 is overall material balance. Okay. In this overall material balance, and we assume that it is a steady state process. Total material in is equal to total material out. So, Q 0 is equal to, so Q is equal to Q 0 plus Q prime. Okay. Q is total material going into Q 0 plus Q prime, and we are assuming that the density remains constant for all these streams. Okay. Density of all streams are equal and constant, they do not vary over the length of the membrane. So, this is one equation. Then you do overall second equation, that is overall A balance. Total A in, total A out. Q is the flow rate multiplied by the mole fraction of A, that is Q times x, that is going into the system. Q 0 is the reject flow rate multiplied by the mole fraction of the reject stream, plus Q prime is the flow rate of the permeate that is going out with the composition y. Okay. So, that is the total A going out. Now, this is overall A balance over the differential element. Now, if you do that is the overall balances. Now, if we do the differential balances, so whatever we have done till now over the element, we are doing the overall balance. Now, we can do the differential species balance over the differential element. Over the differential element. What is the differential element? Differential element is between dAm and this Am and Am minus dAm. In the earlier case, it was this was located at the exit point. Now, if you do a species balance overall over the differential element, the A balance will give the following: d of Qx is equal to nothing but d of Q prime y. Okay. So, what is the depletion in the feed site? That will be the gain in the permeate site. Okay. So, if the overall the differential balance will be schematically can be shown like this. This is the area A dAm, there is nothing but Am and Am minus dAm. So, this area is dAm. Now, Q and x is going into the system, and what is going out is Q minus dQ is the flow rate, because some amount of permeate is going out, and since it will be depleted in x. So, x is the mole fraction of the component A. So, x minus dx will be going out, and let us say this is the differential element of the membrane, and dq is the gain in the flow rate in the permeate stream, and y is its composition. Okay. So, this will be the differential element, differential balance over the differential element, and this schematic gives differential element with various streams. Now, if we really do that, the A balance gives you q times x is equal to q minus dq into x minus dx plus y times dq, and if we just simplify this equation, this gives you y dq is equal to differential of q times x, right. And you can have a local flux of A across the membrane. The local flux will be the permeability of A divided by the thickness multiplied by the delta P. Delta P is the partial pressure of A in the feed side minus partial pressure of A in the permeate side. So, if you would like to find out the local flux of A across the membrane, this gives you minus y dq is equal to P A prime by T, T is the thickness, multiplied by P H times x minus P L times y multiplied by d A. Okay. And local flux for species B across the membrane can be given as minus of 1 minus y dq is equal to P B prime over T P H 1 minus x minus P L 1 minus y d A. Now, if you combine these two equations like earlier, that means you divide this equation by this equation, you will be getting a relationship between y and x with the various PL and pH ratio and the permeability ratio. That means, if you divide species balance of A by species balance of B, you will end up with the following expression: 1 minus y by 1 minus y is equal to P A prime by P B prime x minus P L over P H times y 1 minus x minus P L over P H into 1 minus y. Now, q prime can be eliminated. So, in the earlier equations, I think we have if you go through the sequence of equation, you can find out from which equation q prime can be eliminated from this q x is equal to q 0 x 0 plus q minus q naught times y. Okay. 5.17 and 5.18. So, okay. So, this is the from the overall material balance and overall A balance. From overall material balance and from overall A balance, one can eliminate q prime, and this equation can be rearranged and this can be written as q naught is equal to q into x minus y divided by x naught minus y. Okay. Now, this equation can be substituted in q. The earlier equation, this equation can be substituted in place of q. That means, the earlier equation was q naught is equal to q into x minus y divided by x naught minus y. So, you can get the expression of q in terms of q naught as x naught minus y divided by x minus y. So, this can be substituted in the local flux equation, which is nothing but a differential equation. If you do that, you will be getting minus y d dam times q naught x naught minus y divided by x minus y, okay, is equal to p a prime divided by t p h x minus p l y. Okay. So, this can be further simplified as minus y q naught d x naught minus y x minus y within bracket dam is equal to p a prime by t p h x minus p l y. Now, we take the we differentiate this equation and rearrange. In this case, both x and y are function of am, because they are varying as a function of the length. So, if you do that, if you carry out this differentiation, then what you will be getting, and rearrangement, you will be getting q naught times y into x minus x naught dy by dam minus x naught minus y dx by dam is equal to p a prime by t x minus y p h times x minus p l times y, and you have the relationship between y and x as the relationship is 1 minus y divided by 1 minus y is equal to alpha star x minus r y divided by 1 minus x minus r into 1 minus y, where r is nothing but the ratio of lower to higher feed side pressure. Now, this equation can be simplified as y into 1 minus x minus r y minus y square is equal to alpha star 1 minus y x minus r y. So, you can differentiate this expression with respect to a m. So, these are all mathematical jugglery basically. Differentiate with respect to a m, what you will be getting is that you will be getting an expression of dy dam in terms of explicitly dx dym, that will be substituted here. So, you will be having only one differential equation dx dim. Okay. So, dy dam will be nothing but y plus alpha star 1 minus y divided by 1 minus x minus r 1 minus 2 y plus alpha star 1 minus y times r plus alpha star x minus r y. Multiplied by dx dam. So, these can be substituted in this differential equation. So, it will be basically in terms of dx dam only. So, this can be written as beta times dx by dam. The whole term is a beta, and beta is a function of both x and y, and the parameters were r and alpha star, and r is nothing but the ratio of the pressure in both the chambers. So, one can express dy dam in terms of dx dam, and dx dam can be rearranged as p a prime over t x minus y x p h minus y p l divided by q 0 times y x 0 minus x minus beta, which is a function of both x and y, x 0 minus y. Okay. Now, so this is the expression of different of dx dam. Similarly, from the local flux equation of the species balance of species B, from local flux equation of species B, you can obtain an expression of dy dam. Okay. Let us say this is G1 as a function of x and y, will be obtained as G2 as a function of x and y. Now, these two equations are ordinary differential equations, and you know the what are the composition at the inlet, okay, and they can be solved simultaneous differential equations, simultaneous nonlinear, okay. In fact, there are ODEs, and you can march forward and using a Runge-Kutta 4 method, we can really solve it numerically. Now, you can get different values at the end points. The values at the end points can be obtained by overall balances. Because that is important. Overall material balance is given as Qf is equal to Q0 plus theta times Qf. Okay. So, theta is the cut ratio and Q0. So, therefore, Q0 is nothing but 1 minus theta times Qf, and overall A balance will give you Qf xf is equal to Q naught x naught plus Qp prime Yp, that we have derived earlier. Yp is equal to xf minus 1 minus theta x naught divided by theta. Okay. Now, for a given value of theta, what you have to do? You have to guess a value of x naught, that is the composition at the reject stream at the outlet. Then you have to solve Yp from this equation. Okay. Now, check the solve differential equations, ODEs, and calculate Yp, okay, and check the value of Yp that you are getting from step number 3 is coming close to step number 2 or not. If not, if yes, fine. So, so you compare these two values, Yp from step 2 minus Yp of step 3, mod of that, whether that is less than epsilon or not. If yes, fine, otherwise you have to guess a value of new value of x naught. Okay. That is how this counter current flow configuration of gas separation will be using a membrane system will be conducted. Now, this will be definitely a material which cannot be done in a class. So, one has to go for the numerical technique, and if you are really interested, you can formulate a problem and really solve this problem. Now, this material has been taken from the book of Jinkoplis, Transport Processes and Unit Operations. So, if anyone is interested, you can go through this book and just take up the typical values. They have given several problems of this type of things. So, just take up the relevant data and try to solve this problem numerically. Okay. Now, next what we are going to do will be based on the principles that we have already said. I think if you can remember that the first two flow configurations can be solved analytically. Okay. So, I will be taking a couple of examples and try to solve in the class to demonstrate how these design equations will be utilized to design a real gas separation system. So, the first problem is example 1 is it is dealing with a separation. Suppose you have a mixture of gas A and B, it is a binary mixture of A and B in feed stream. The feed flow rate is given as QF as 10 to the power 4 centimeter cube at STP, standard temperature and pressure, that is 1 atmospheric pressure and 27 degree centigrade. QF is 10 to the power 4 centimeter cube per second, and feed composition that is going into the system is 0.5. That means, you have a mole fraction of a 0.5 in the that is going into the system, and the desired composition of the reject is given. X naught is desired composition of reject, that is given as 0.25. So, you have set what will be my reject composition. So, you have to design the system, because you have to find out what is the required membrane area for this particular application. The membrane thickness is given as T, membrane thickness is given as 3 millimeter. That is not 3 millimeter, 3 into 10 to the power, it will be further less. So, it is given as 3 into 10 to the power minus 3 centimeter. Okay. pH, the feed side pressure is given, (80 centimeter mercury). Okay. PL, the permeate side pressure, that is 20 centimeter mercury, and the permeabilities of two species they are given. Pa prime is permeability of species A, and this is given as 60 into 10 to the power minus 10 centimeter cube at STP multiplied by centimeter divided by second centimeter square centimeter mercury, and Pb prime is permeability of species B, and this is given as 6 into 10 to the power minus 10 of this unit. It is the same unit. Okay. Now, you have to assume a completely mixed up model. Assume complete mixing model. Calculate Yp, that is the mole fraction in composition in the permeate, mole fraction of A in permeate, theta, that is the fraction permeated, and third, the membrane area required for this purpose. Okay. So, let us look into this problem. So, it is a completely mixed up model. So, we have all the design equations we have. Let us write down what are the various values of the parameters are known to us. Okay, there are 7 variables, some 4 are known. So, xf, x naught, fit composition is known to us, x naught that we have set, that this is the composition of the reject, alpha star, that is the ratio of permeability of A and B, that is known, PL by pH, the operating conditions are given. So, all these 4 parameters are known. Okay. And what we have to determine? We have to determine Yp, that is the composition in the permeate, theta, the cut ratio of the feed that is going into the permeate, and membrane area that is required, that we are going to find out from this solution. So, if you remember the design equation of permeate composition, the permeate composition was given as Yp is equal to, in the form of a quadratic, minus B plus B square minus 4 AC divided by 2 A, and we talked about it was a quadratic, and these ABC are the various parameters which relate the operating on known values. A is nothing but 1 minus alpha star, B is equal to your pH over PL 1 minus x naught minus 1 plus alpha star pH by PL times x naught plus alpha star. Your C is minus alpha star pH by PL times x naught, and your alpha star is PA prime divided by PB prime. So, this is 60 into 10 to the power minus 10, and this is 6 into 10 to the power minus 10. So, this value will be 10. That means, permeability of A is 10 times larger than that of B. So, more A is expected to be in the permeate compared to B. Okay. Let us find out the other variables. So, A is 1 minus alpha star. So, it is 1 minus 10. So, it will be minus 9. B is pH over PL 1 minus x naught minus 1 plus alpha star pH by PL x naught plus alpha star. So, this will be 80 divided by 20 into 1 minus 0.25 minus 1 plus 10 into 80 divided by 20 into 0.25 plus 10, and if you calculate this value, it turns out to be 22. Okay. Now, if you put the value of C, C becomes minus alpha star times pH over PL over x naught. Put the values, this turns out to be minus 10, 80 by 25, 20 into 0.25. So, it turns out to be minus 10, and now if you put the value of ABC in the expression of B square minus B minus B square minus 4 AC divided by 2 A, this turns out to be 0.604. Okay. So, x0, you have xf, this relation xf minus theta times yp divided by 1 minus theta. So, you have calculated yp, you know xf, you know x naught. So, you can calculate the value of theta, and theta turns out to be 0.706. So, for this particular problem, 70% of feed can be recovered in the permeate, and the expression of AM, if you remember, it was theta times QF times yp divided by PA prime divided by T into pH x naught minus PL yp. Now, if you really put all the values, this turns out to be 2.7 into 10 to the power 8 centimeters square. Okay. So, this is a typical order of magnitude of membrane area that you are looking for this particular problem. Okay. So, relevant configuration can be the module can be prepared by ensuring that this much of membrane area you will be getting in this system in order to get this system feasible. Okay. So, in the next class we will be I have decided to solve one more problem, and for the this type of system, and then we will move for the next topic, that is the surfactant enhanced separation processes. Okay. Thank you.